For decades, the narrative around climate change has focused heavily on the dangers of rising carbon dioxide. It is pushing our planet toward an irreversible tipping point, a runaway greenhouse effect, similar to what occurred on Venus. But what if that fear, though well-intentioned, overlooks one of the most fundamental aspects of Earth's history? What if the very rocks beneath our feet tell a story that disproves this alarm? That story is found in limestone, a rock that may hold the key to understanding why Earth is protected from a runaway greenhouse scenario, no matter how much fossil fuel we burn. To understand this, we must first go back to the beginning. Earth formed approximately 4.5 billion years ago from the debris of a supernova that once exploded in our galaxy. In its early stages, Earth was a hostile place, a ball of molten rock with no atmosphere, no oceans, and no life. Over time, volcanic activity created the first atmosphere by spewing out massive amounts of gases, including water vapor, methane, ammonia, and carbon dioxide. The scale of carbon dioxide in the early atmosphere was staggering. Some estimates, such as those by Kasting and Ackerman in 1986, suggest that atmospheric CO2 could have been as high as 10 bars, or about 1 million parts per million, more than 2,300 times today's level. If carbon dioxide alone was sufficient to cause a runaway greenhouse effect, it would have happened then. Earth was enveloped in a thick CO2-rich atmosphere under constant volcanic bombardment, with no oceans or vegetation to absorb any of it. Yet, no such runaway effect occurred. The Earth began to cool, the crust formed. Oceans condensed from the vapor, and conditions slowly stabilized. If Earth could survive that, with 1 million ppm of CO2, how could it spiral into runaway greenhouse now, with just 420 ppm? The story doesn't end with cooling. Around 3.7 billion years ago, something extraordinary happened. Life began. The earliest forms of life were prokaryotes, single-celled organisms that fed on carbon compounds in the oceans. These primitive microbes played a vital role in the planet's carbon cycle. As they died, their cellular remains settled to the seafloor, mixing with sediments. Over time, these deposits compacted and mineralized, creating the earliest forms of carbonate rock, including limestone. But there's more. Much of this early limestone didn't survive in its original form. It underwent a process known as diagenetic replacement, where calcium carbonate was gradually replaced by silicon dioxide, forming rocks like chert. This process, while releasing some CO2 back into the atmosphere, still marked the beginning of Earth's immense natural system of carbon sequestration. Rocks began pulling CO2 out of the sky, not through technology, but through biology and geology acting together. Evidence of this process has been found in rocks over 3 billion years old. Studies by Francis Westall and Shuhaizi in 2020 showed that the Mushandike limestone in Zimbabwe, dating back to 0.8 billion years, has organic origins. Another study by Abigail Allwood and colleagues in 2007 identified stromatolitic structures formed by microbial mats in the 3.43 billion year old Strelley Pulchert in Western Australia. These findings confirm that carbon-based life was actively transforming the atmosphere billions of years ago, long before the rise of complex life. Then came photosynthesis, the game changer. Cyanobacteria developed the ability to harness sunlight to convert carbon dioxide and water into glucose, releasing oxygen as a byproduct. This not only drew down even more atmospheric CO2, but also laid the foundation for an oxygen-rich atmosphere. Between 2.4 and 2.3 billion years ago, the Great Oxygenation Event allowed for the evolution of oxygen-breathing organisms, and eventually led to multicellular life. About 1.5 billion years ago, algae appeared, further accelerating the process of CO2 capture. These and other microorganisms continued sequestering carbon into organic matter and carbonate deposits in the ocean. The greatest leap came around 540 million years ago, during the Cambrian explosion, when shell-forming sea animals evolved. These creatures extracted calcium and carbon from the ocean and built shells of calcium carbonate. When they died, their shells fell to the ocean floor, building thick layers of limestone, vast carbon storage units, courtesy of biology. Over hundreds of millions of years, Earth has evolved an extraordinarily effective carbon sequestration system. Over 90% of all CO2 ever present in Earth's atmosphere has already been locked away, mostly in limestone. This natural process has removed thousands of gigatons of CO2, far more than humanity could ever emit. Today, limestone covers approximately 12.5% of Earth's land surface, a testament to billions of years of life cycling carbon into long-term storage. Dr. Johnson Haas, a geochemist at Western Michigan University, noted in 2017 that shell-forming organisms remove about 0.03 gigatons of carbon from the atmosphere annually. At that rate, they could deplete all atmospheric CO2 in less than 1 million years, if not for ongoing volcanic activity and the weathering of rocks, which return small amounts of CO2 back into the air. This dynamic balance, absorption and replenishment, is what maintains Earth's climate stability. Even with fossil fuel burning, the total human contribution to atmospheric CO2 is tiny compared to the volumes locked away in rock. Moreover, not all shells become limestone. Those that fall below the carbonate compensation depth, about 3,500 meters, dissolve in the deep ocean due to pressure and acidity, releasing their carbon back into the water and eventually into the atmosphere. This too is part of the natural balancing act. And this is where the comparison with Venus fails. Venus has no limestone, no oceans, no biosphere. Its surface temperature is over 460 degrees Celsius, and its atmosphere is over 96% CO2, but not because of human activity. Venus never developed the biological or geological systems to sequester carbon. Without oceans or limestone formation, there was no way to regulate CO2. Earth, by contrast, is alive, and it's life that has pulled carbon out of the air and locked it away. In fact, the Earth is now dangerously close to the minimum CO2 levels necessary for plant life. During the last ice age, CO2 levels dipped below 180 ppm, only a fraction away from the extinction threshold for plants, which is around 150 ppm. That's why commercial greenhouses often add CO2 to stimulate plant growth. It's not a pollutant, it's a vital nutrient, and historically, Earth has had much more of it. The ultimate irony is that CO2, long feared as the villain of climate change, has always been the hero of Earth's biological history. Without it, no photosynthesis, no oxygen, no life. And without limestone, born of the death of uncountable marine organisms, Earth might truly have faced a Venus-like fate. But the very existence of limestone proves that the planet has not only survived extreme CO2, it has thrived because of its ability to store it. To claim that burning fossil fuels could cause a runaway greenhouse effect is to ignore billions of years of geological evidence. Even if we were to somehow extract and release all the carbon stored in fossil fuels and limestone, a physical impossibility, we would still fall far short of the CO2 levels Earth once had. And there was no runaway effect then, there will not be one now. So when we speak of climate, let us not be driven by fear alone. Let us be guided by deep time, by the story told in the rocks, in the fossils, and in the chemical archives of Earth. The Earth is not fragile. It is a system built to self-regulate, designed by the interplay of life and stone. And its limestone bones hold the final proof. The runaway greenhouse effect is not our destiny, it is a myth.